All right, guys, here we go. Diagonals, right? Cardinal rules of carpentry, which were what?
Level.
It's an acronym.
Square.
PLS, right?
Plumb level squares.
Plumb level squares. PLS. Also, too, if you work around lasers, right? A PLS is also a type of laser, right? It could be a line laser. Okay. Beautiful. Okay. Here we go. This is the math for the week. This is the only math we're going to go ahead and actually cover, I think, today. I want to say that's all we got today. Okay. PLS, plumb, level, and then square. Okay. Now, that being said, by the end of this presentation, we're going to be able to cover these two objectives, right? First one was to the apprentice will know what the Pythagorean theorem is and what it's used for in construction. And the second one, apprentice will be able to lay out a right angle that is a perfect square. Dude, if you can't lay out something that is truly square, we have a big problem. We have a big problem, right? I said that when something isn't square, for example, this week we're going to be covering the foundation, correct? If the foundation isn't square, those of you that don't know what a foundation is, or what's a foundation?
It's was cement.
It is, okay. There's multiple types of foundations,
Like the
right?
bottom is the building.
Essentially, it's the footing of the building, okay? You can go ahead and either dig it out, okay? Then you go ahead and pour the footings. You might have a concrete slab, or you might have some kind of a stem wall, right? Okay, you might have a wall. You might have some type of anchor bolts coming up, and then the sill mounts on that, and then you start your framing, right? Okay. Now, if this foundation isn't truly square, we have a problem. The framers are going to struggle. The ones doing the siding are going to struggle. Everybody struggles. Okay? It needs to be square. Now, whenever we're talking about square, we're talking that it has to be a perfect what? Angle. But what's the angle? Correct. Yes. 90 degrees. 90 degrees. Guys, 90 degrees is everywhere. Check it out. How many 90 degrees do you see in this room? It's a lot. Everywhere. Everywhere, right? You see it in the TVs, this whiteboard, the ceiling. It's everywhere. Everywhere, right? So what are we saying? We're saying that square refers to this angle here, which would be 90 degrees. Okay. You guys ever heard of Pythagorean?
I've heard of it.
You've heard of his theorem, but have you ever actually heard of Pythagorean? So Pythagorean was a Greek mathematician. Okay. He's actually the first one that called himself a philosopher. Okay. So at one given point, he ends up going to Egypt and studies with them. Right. Mind you, the Egyptians had already been using the Pythagorean theorem for thousands of years, right? Because they had already built the pyramids. Fun fact, you know how out of square the pyramids of Giza are? How many inches are they out of square? They're like 5.5 inches out of square. That's amazing. That's amazing. That they're only 5.5 inches out of square, right? For not having the technology that we have now. Now we have modern day technology, and shoot, for a building like that, it can happen that you're that much out of square, right? So anyway, Pythagorean ends up going with the Egyptians, and as a matter of fact, one day he was going by the blacksmith shop, right? And he noticed that the iron worker was banging on the anvil, but that it didn't always emit the same frequency or the same noise. So whatever he did, he ended up going into that iron worker shop, and then he realized that math, or that songs, are mathematical, right? Are there any musicians in here? Then you would know that it is mathematical, right? There are certain sequences and things like that, right? So that was Pythagorean. He ends up going back to Greece, and guess what he took with him? The theorem. And guess what he called it? The Pythagorean theorem, right? Because he was a philosopher, right? So anyway, he ends up going back to Greece. He starts his own religion, right? Okay. Fun fact, there was a lot of things that he couldn't do in his own religion. Like, for example, he couldn't grab a sword and like stick it in the fire. There were certain things he couldn't eat. And guess what they worshipped? Triangles. We should that fool saw triangles all crazy. Probably LSD or mushrooms at the time, yeah. So anyway, what's the theorem? Here we go. Okay, important. You guys have your packets in front of you. You guys want to go ahead and follow along so you guys can see what I'm talking about? Open up your packet, and it should be what we call diagonals. Should be on page 55. Looks like so. Looks like so. Diagonal. So what's the theorem?
A squared plus B squared equals C squared.
A squared plus B squared equals C squared. Okay. There is a square root somewhere in this, but we'll go ahead and talk about it later. Whenever we're talking about this theorem, we're directly talking about a triangle. Okay? We're talking about a triangle. Okay? In a triangle, there are three main components. Okay? In a triangle, there are three main components. Okay? This would be the rise. This would be called the run. And does anybody know what the mathematical term for the long side of a triangle is called? Starts with an H. Hypotenuse. Okay? It's called the hypotenuse, but I can't spell it, so we're going to go ahead and call it a diagonal. No, I can spell it. I'm the 6th grade spelling bee champion. In Spanish. I went to a bilingual school. I didn't speak English until I was like 13. Yeah. So, okay. Good? Good? This is A, this is B, and this is C. Okay? Now, don't let your math teacher fool you. Okay? For what we do, for most operations, the rise and the run are interchangeable. What is not is the diagonal. Okay? The hypotenuse will always be the long side of a triangle. So how does this apply? Okay? Let's go ahead and take this whiteboard, for instance. And the goal is to see if this degree right here, everybody see the 90 degrees?
Yeah.
If it truly is square, that'd be the term, right? So can I get two measurements from here? Yeah, absolutely, right? My first measurement would be from here to here. And then my second measurement would be from here to here, right? Okay? So let's go ahead and call this one 5 feet. Okay? 5 feet. And we'll go ahead and call our run 8 feet. Okay? So then how would we plug it in, right? Remember I said this is my rise, so it would be 5 squared plus 8 squared would equal C. 5 times 5? 25. 8 times 8? Okay. So now we're going to go ahead and add those two numbers. 25 plus 64, which I want to say is going to be 89. Yeah, is that correct? Good. Okay. 89. Remember I told you there was a square root somewhere? Here it is. This number needs to be square rooted. So go ahead and open up your calculators. Okay? Just your regular calculators. If you have an iPhone, all you have to do is put it on its side. Okay? And what you're going to do is you're going to go ahead and square root that number. Okay? I think first you would hit square root and then 89. And then 80 or 89. And then square root. Yeah, that's one. Yep.
Which one?
That has 2. Okay. So far so good?
That's the theorem.
That's what we should have. That's what we should have gotten. 9.43. Okay. So far so good? Now that is in what unit? 9.43. Can you read that in a tape measure?
Yes.
Okay, easy. I can't. I can't. Unless you have a chart like the one I have in the back, right? 9.43. How would I convert that into something that I can read in my tape measure? Times 12, times 16, right? So this would come down, right? This stays. This is 9 feet. So I'm going to go 0.43 times 12. Somebody do it. 5.40, sorry, it would be 0.43 times 12. What do we got?
5.16.
5.16, so it'd be 9 foot 5, and then 0.16 times 16.
2.56.
So does it stay a 2 or does it go to 3? It goes to 3, right? So then the answer, my diagonal answer would be 9 foot 5 and 3/16. So when I get my tape measure, if my answer isn't 9 feet 5 and 3/16, am I square? No. It has to be this number, no matter what. Let's say my number was 9 foot 5 1/4. Then how out of square am I? At 16. So far so good? Everybody understand the concept, right? What we're trying to achieve is our diagonal number. There's always a diagonal in a square, and there's always a diagonal in a rectangle. Really, what composes a square?
2 triangles.
2 triangles. What about a rectangle? It's the same thing. What we're trying to achieve is the diagonal distance from here to here, and from here to here. If it does not make 9, 5, and 3/16, then there is a problem. Cool. So far so good?
Do you only multiply by 12 when it's like a decimal like that? Where it's not like an even number? Like just a regular number?
Yeah, because there's a decimal, I need to go ahead and break this down to something that I can go ahead and read and take measure.
Gotcha, because I think number 1 is 39 feet flat, so you wouldn't multiply that.
Okay, we're jumping ahead. Okay.
Sorry about that. I was just a little confused on that.
39 feet would just stay. Correct. That would be the hard answer. Yes.
I had a question to go back to the 25 plus 64. Obviously it's 89, but what do you have to do after that, Stan?
Okay.
89?
I just square rooted it. See the square root? All I had to do was square root it, and that's where 9.43. You see, if you wanted to, if you could read it, you could just leave the answer like that. That is the answer. But is that something that you can go ahead and actually read in your tape measure? No, you can't. You can't. This is the answer, but we're trying to get something that we can read in a tape measure. Follow?
Silly question, what's square root, what does that mean?
Square root breaks it down to a number that can be multiplied by itself. For example, a square root of 9, what multiples would multiply by each other to get you 9? 3. So then the answer would be 3, right? Because 3 times 3 equals 9. Okay, I'll give you another easy one, right? Nobody answer. Tony, what number when multiplied by itself would give you 25? 5. So that'd be the answer. Another one. You can use your fingers. It's okay.
It's a 9?
6 times 6?
Oh, 6 times.
So the square root would be 6,
Oh,
right?
6.
6. Cool. So it's okay. It's okay. You're on camera. You're nervous. All right. Here we go. Cool. Now, how do we actually use this in real life? Okay. Everybody understand the concept so far? Okay. Easy peasy. You'll never. Hopefully, you never forget this lesson. This will follow you your whole career, even if you don't stay in carpentry. You go do some kind of other construction work. It should follow. Yeah.
We're doing concrete right now. That's a whole nother trade in itself.
So it'd be rise, we have the run, right? Okay, A and B. Well, how would you use it in real life? Okay, let's say that I wanted to see if this angle here was truly 90 degrees. Okay, well, 2 ways I could do it. I could go ahead and either pull the measurement from there to here, and from this wall, the north wall, to the south wall, right? And then that would give me my diagonal distance from there to there. Make sense? Or you can go ahead and use whatever's available to you. For example, we can go ahead and take this measurement here. Okay, I'm gonna go ahead and use my tape measure over here. And I have 12 feet. Okay. So then we can go ahead and use 12 feet as my rise. Follow? So far so good? Then I could go ahead and use, kept measuring. We'll go ahead and we call it 19, okay? Everybody know where we got this from, right? I measured it, right? Okay, 12 feet to the, where the mullion starts, and then 19 feet to the edge of this, right? Now I'm trying to get a diagonal distance from here to the mullion over there, right? To where the window starts, right? So then we'll go ahead and plug it in. Back to our formula, a squared plus b squared plus c squared, right? Okay, my a is 12 squared plus 19 squared, and it's going to give a c. 12 times 12? 19 times 19? What do we got, guys? 19 times 19?
61.
Now, all we have to do is go ahead and actually multiply these two, add those two numbers together, right? 144 plus 361 is 504?
505.
505. Okay. What do I have to do to this number? I'm going to go ahead and square root it, right? Okay. The answer would be what? 22. What do we got, Eric? Somebody do it. Square root 505.
How would you do it on the calculator?
If you have an iPhone, take the lock off. Okay. All you're going to go is 505. And the square root function right here. 22.47. Okay. That means that, hold me right there, Eric, at that quarter. Over there, where the, exactly, right? Okay. If my number from there to here is not 22.47 feet, which is roughly going to be what? 22 feet 6 and 5/8? Something like that? 22 feet 5 and 5/8 to here, then am I truly square? No. Can you guys see the right angle? You see it? What I'm trying to do is to make sure that these walls truly do make two angles, right? That sum up 90 degrees. That's what I need to get. Okay? I need this to be 90 degrees. If it's not 90 degrees, then am I square?
No.
No. No. How do I do that? By getting measurements. Okay. So far, so good? Okay. Let's go ahead and do some more examples. I'm going to go ahead and throw up some numbers on the board. Yeah. Square root. On that one, you are going to go and you're going to go, for example, let's say 45. Convert arrow. Convert arrow. Convert arrow. Okay. So let's go ahead and do a sample problem, yeah? Okay. Okay, here we go. Five feet, 12 feet. And then I am gonna give you, we can do that one, yeah. Let's do it, guys. So we have 5 foot rise, 12 foot run. Plug it in into the theorem. All it is just plugging it in, yeah? See what we come up with. Yeah. How do you what? Yeah. On the calculator? Yeah, because it's squared, right?
Yeah.
Whenever something is squared, you're just multiplying it by itself. Yeah?
That does,
Yeah, Eric.
Yeah,
Yeah, that's it. That's it. If you have a decimal, right? Let's say the decimal had been, I don't know, 13.75. You could read the 13, but can you read the 0.75? No, right? You wouldn't need a chart like that, right? So you need to break down 0.75, multiply it, but that's already too much information for right now. Oh, okay, Anna.
I was just, see it.
Yeah. So let's go ahead and do it, yeah? This is A, this is B, and this is C, correct? So A squared would be what? 5 squared. And then B, be 12 squared, right? So 5 times 5? 12 times 12? Okay. You add those up, and it should be 169, correct?
Correct.
Remember, this is in a square root, so the answer should be 13 feet. The hypotenuse, the diagonal on the long side of this triangle is 13 feet. Cool? Easy peasy? Does everybody understand?
Yes.
Now, when I go ahead and measure this distance on my triangle, if I don't have 13 feet, then am I truly square? No. As a matter of fact, you can even use the Pythagorean theorem to essentially tell you if this wall is plumb. Can you guys envision a triangle here? Yeah, absolutely, right? This can be your rise, this could be your run, and now I would have to go ahead and select, calculate my number to the top of that wall, right? That's another good way to check if you're truly plumb, right? Okay, we can go ahead and check like that.
Question. Sometimes, no, this way, crazy.
It's okay, say it. I like crazy.
So, okay, so sometimes you see when you're forming.
Yeah.
It's okay if you're like 116 off or 116.
There are, okay, so there are tolerances. There are tolerances.
Yeah.
But right now, we're not worried about tolerances. Right now, we're worried about calculating it mathematically. Yes, in concrete, there's a tolerance. Concrete like a quarter. A framing, it gets less, an eighth. Finish work, 16/32, yeah? So there are tolerances, yeah? But mathematically, this is the number we're trying to achieve. Cool, so far so good? Now check it out, I'm gonna go ahead and back to telling you a story, yeah? Okay. Now, I don't know when, but somewhere along history, one of our carpenter's brothers or sisters said, you know what? To that theorem, I could go ahead and plug in the following three numbers. 3, 4, and 5. Have you ever heard that? 3, 4, and 5. Okay. Now, essentially what it becomes is a generic number. Okay. That whenever you plug it into the theorem, it truly does work. Okay. So if I were to plug in 3, 4, it's always going to go ahead and work itself out to be 5. Okay. Somewhere along history, somebody said, hey, let's go ahead and plug in the next sequential orders for a theorem. And I'll explain to you how 3, 4, 5 works, yeah? So we would have 3 squared plus 4 squared is going to give us C. Okay. 3 squared, 3 times 3? Plus 4 times 4? 16. 25, remember. What do I need to do to this number, Tony? Square root it. What number, when multiplied by itself, is going to give me 25? 5. The answer is 5. See that? This always works. Now, the beautiful thing about 3, 4, 5 is that you can go ahead and increase it or shrink it to whatever your needs are. So essentially, you don't have to go ahead and plug in the same exact numbers. I can just go ahead and plug in a multiple of 3, 4, 5, and it would work. Okay? Let's say 3, 4, 5, right? we'll call this from here to here 4 feet, from here to here 3 feet. Those numbers are way too small. Is it gonna be accurate? No, no. The longer the distances, the multiple of 3, 4, 5 needs to be increased, right? So I need to go ahead and increase 3, 4, 5, right? Okay? Couple ways you can do it. You're gonna hear a few things, okay? As long as you multiply 3, 4, 5 by the same multiple, it will increase itself symmetrically, yeah? So for example, to 3, 4, 5, let's say I needed a bigger number. I just multiply by 2. So now that would be, the next version of 3, 4, 5 would be 6, 8, 10. Is that not big enough? Okay, you want to go ahead and increase it more? Guess what? You can just multiply it by 2 again. Okay, so the next version of 3, 4, 5 would be what? 12, 16, 20. Not big enough? Do it again. And again, right? So it'll be 24, 32, and 40. How does this apply? Well, back to our triangle. If we increase 3, 4, 5 to something that would truly work and be more accurate now, I would go ahead and use 24 feet, 32 feet, and then my diagonal would be 40. Without having to actually plug it into my calculator, just using 3, 4, 5. You know what's beautiful about 3, 4, 5? To 3, 4, 5, you could just add zeros and that will work as well. Okay, prove it to yourself. Go ahead and do it. Plug in 30, 40, 50 into the Pythagorean theorem, yeah? Okay. So now we would go 30 squared plus 40 squared, and let's go ahead and do that, yeah? Okay. 30 times 30? 40 times 40?
1,600.
Now we're going to go ahead and sum those up. What do we get? 2,500, correct? Everybody follow? We're all on the same page? What's my next step, William?
What's it called? The root square?
Square root it, yeah? 2,500, I'm going to go ahead and square root that. Sure enough. What do we get? 50. Okay, so far so good. I prefer you right again. Okay, beautiful? So far so good? Now, the beautiful thing about 3, 4, 5 is, remember I told you that you can also shrink it? Right? What you could do to 3, 4, 5 is just cut it in half. Okay? So if I were to cut 3, 4, 5, then the next version of that would be 1 foot 6, 2 feet, 2 foot 6, or 30 inches, yeah? I'll cut it again. Half of 18 inches? 9 inches, 12 inches, 15 inches. Yeah, so far so good. 2 foot 6 is 30 inches, correct? 24 plus 6, half of that is gonna give me 15 inches. Cool, beautiful what you can do, right? Okay. Now, a lot of old timers are just gonna wanna multiply 3, 4, 5, just times 2. Remember I told you? You guys remember that? We went 3, 4, 5 times 2, got us to 6, 8, 10, 12, 16, 20, so on and so forth. The reality is that to 3, 4, 5, you can multiply it by any number as long as it's the same. And it works, and we just proved it to you. Because what did I multiply it by to get me to 30, 40, and 50? 10. Did it work?
Yeah.
Yes, absolutely. I could have multiplied this by 7, and it will always work. I could have multiplied this by 6, and it will work. That is the beauty of 3, 4, 5. How do you guys feel? Good? An understanding of what it is? Okay, so right now we're going to go ahead and do it on our papers, okay, we're gonna go ahead and do the math problems, check it out. If you open up your exercises, okay, diagonals on page 55, right? Problem 3, you're gonna find a challenge. Can you go 3.9, William? Everybody on problem 3? Everybody see it?
Yeah.
Can you go ahead and put 3.9 on the calculator?
No.
No, right? Because if you look at your chart, 3.9 is what? 10 3/4-ish? What do you need to do to that 3'9" to get it to a decimal?
You guys inches?
You need it to feet. To feet. Follow? You can either work all in inches or all in feet. But you can't do inches and feet. It's either or. But whenever the result spits out, it's gonna go ahead and be in the result that you multiplied it by. Follow? Let's say you had 24 inches, 32 inches, then guess what? The diagonal has to be in inches as well. It has to be. You can't do 24 feet by 32 inches. That's crazy. That's crazy, right? Okay. Good? So what am I gonna do to that 3'9" to get it to 3.75? That's the answer, right? What do I need to do to that 9?
Divided by 6. What, feet 12?
Divided by 12. Right. Correct, right? Or look at the chart in the back. Right? Good. All right, let's go ahead and try it. Okay. So what are we gonna do? Now that we got the diagonal of 14 feet 5 and a 16th, right? Okay, again, I'm gonna explain to you the process of what's gonna happen. Okay? For those of you nervous or worried about the test tomorrow, don't be. But you should go home and study the diagonals. We'll take the test, no, we'll take the, I don't think you guys are ready. I'm gonna give you guys, some of you guys time to study, take it home, and tomorrow morning be ready for it, cool? What was gonna be the first step? Eric, for me to snap this out in real life, what was the first step?
Put it into the
Pythagorean theorem, right?
Theorem, yeah.
Okay, so we need some pieces of information, right? My diagonal, 14 feet 5 and 1/16, yeah? And the blueprint of my project is 8 by 12, correct? The first step was what, De La Mora? To actually snap it out in real life. The first step, snap a line, correct? As long as it doesn't catch a rock, as long as it doesn't catch a nail, that should be straight, correct? Okay. Snap a line. You probably should write that. Snap a line. Okay. Once you snap a line, what dimension can I go ahead and pull?
3, 4, 5.
12. 12. You could, if you were gonna do it that way, right? But we're gonna go ahead and use the exact hypotenuse or diagonal in our rectangle, yeah? So from my point of origin, or where I wanna go ahead and actually begin, I'm gonna go ahead and pull 12 feet, okay? Now remember I told you that the rise and the run are interchangeable. Could I easily have pulled 8?
Yes.
Yeah, it doesn't matter, right? Because the diagonal is not gonna change, right? So I went ahead here, I measured. This distance is now 12 feet. So far so good? Okay. That takes care of the rise. Now I'm gonna go ahead and deal with the run. What is it that I'm gonna go ahead and arc? 8 feet, correct. From my point of origin, I'm gonna go ahead and arc, and that arc is gonna be 8 feet. Cool? Now remember, this line is perfectly straight, correct? What number am I gonna go ahead and arc so that they go ahead and actually intersect?
14.
Exactly. From this straight line, from the measurement 12 feet, I'm gonna go ahead and arc 14, 5, and 1/16. Wherever these intersect, I'm gonna go ahead and pass my chalk box from here, snap it past, and now that will be a true 90-degree. Cool. So Benjamin, what would be the step for me to go ahead and actually zero out or finish my rectangle? What would I have to do? Okay, somebody help him out. One.
What was the question?
How would I finish a rectangle?
Do the same thing you did on this side, but
Correct. Because it's a mirror, correct? I told you that a square is really just two triangles. I told you that a rectangle is really just two triangles, right? So from here, what's the dimension I'm gonna go ahead and arc? Diagonally. From this corner, right? 14.5 and 1/16. Now I'm gonna go ahead and arc another number. What's this number that I'm gonna arc? 8, right? From here, I'm gonna go ahead and arc 8. And at this point, all I'm doing is connecting the dots, right? I'm just gonna go ahead and snap a line from here to here, and then from here to there. And now, I'm gonna go ahead and back check myself before I build. Make sure that diagonally, I have a dimension of 14.5 and 1/16 going both ways, zeroing it. So we said that the first step was gonna be what? Snap a line. You already know your diagonal, which is what? 14.5 and a 16. And then you're just plugging this in and arcing it, right? Friendly reminder. This is what we call the dumb end of the tape, correct? This always stays. This always stays. And this is the one that's always gonna go ahead and arc. Okay? That one's always stationary. So if I were to arc here, this stays here, and this is gonna be the one that arcs. Always, always. Why? Because it's gonna be a lot more comfortable for you to arc. Remember I told you? First you mark, and then you arc, right? Let's say I wanted to arc at 2, I'm gonna make a mark. Bring my pencil to it, and it goes underneath. I can do this all day. Again, this is the dumb end of the tape. The dumb end of the tape is gonna stay, and this one is gonna be the one that does all the action. Cool? Beautiful. Valentin, you got a question?
I'm gonna have streamline.
You have a chalk box. You have a chalk
I'm
box.
gonna use the chalk box.
Monday?
I'm gonna use the chalk box.
Today, you're gonna have an opportunity to use a chalk box. I'll show you. Any other questions? Cool. All right, guys, so do you feel that we know what the Pythagorean theorem is used for in construction?
Yes, sir.
What is used for, Eric?
to find, or to make a square.
It is, right? To make sure that we have a 90 degrees. Cool. So now we're gonna go ahead and head to the shop, and let's go ahead and snap it out ourselves. I'll snap one out, and then you guys can follow along. Cool?